Hello everyone, I am Dr. Osman reporting once again from the University of KwaZulu-Natal, the premier university of African scholarship. In our previous lecture, we looked at energy balancing in reacting systems. We focused mainly on developing our concepts, and of course our concepts are the enthalpies of reaction, enthalpies of formation, and enthalpies of combustion. Today we extend our knowledge into the application, and we look at various examples, solving various energy balance examples for reacting systems. So let's get straight to it. Now at this point you have been looking at various equations, and there's of course lots of summations and changing between temperatures. So it might be a bit complicated for you at this stage. So let's look at a simple illustration. Okay, so let's consider this entire box here to be a reactor, and I have multiple streams coming in and multiple streams going out. Okay, and let's say my streams are at 100 degrees Celsius for the inputs, and the output is perhaps 250 degrees. Now the total difference in enthalpy of the output and the input is of course my energy balance. Okay, and that will dictate how much of energy I may need to either input or remove. Okay, in this case here I have 100 degrees input streams, and it's becoming 250 degrees by the time we're looking at our output. So we can expect that our reactions are perhaps exothermic. So we will have to remove heat in this particular case. And how much heat will we need to remove? It's simply the difference between our output streams and our input streams. And remember that we are expressing our enthalpies in terms of a reference. That reference could be 100 degrees, it could be 250 degrees, it could also be 25 degrees. Now what's important is that, let's say we have various species coming in, and various species coming out. Now we have our enthalpy at 100 degrees, and we can express our enthalpy in the form of any temperature that we like. Our reaction need not be expressed in terms of 100 degrees or at 250 degrees. It can be expressed at our reference temperature. Okay, whichever reference temperature that we need or we want to use. So if I say that, well, my reaction is at 100 degrees, so I'm working at a 100 degree line, but now my products are at 250, so I simply have to use my sensible heat and my latent heat to get up to that 250 degrees. Okay, so don't get confused about the reaction temperatures, because that is simply based on my reference. Whichever reference temperature I use for my particular unit, my reaction can be evaluated, my delta HR can be evaluated at that reference temperature. And if there are many different reactions, I can simply evaluate all of my reactions at the same reference temperature. If I choose my reference temperature to be 100, I'll evaluate all of my reactions at 100. If I choose it to be at 250, I'll evaluate all of them at 250. And no matter the difference, I will have to use my sensible heat, my CP values, and my heat of vaporization if necessary to bring it to the actual temperatures of my outputs or inputs. Now let's say, for example, I chose a reference temperature that is neither 100 nor 250. Let's say if I chose a reference temperature of 25 degrees. Then the enthalpies of these streams here will be stated in reference to 25 degrees. The reaction as well will also be stated in reference to 25 degrees, and the products will be referenced to 25 degrees. And the reference is simply a case of using my CP values and my heats of vaporization if necessary to get from my input to my output temperature. Okay, so hopefully that will clarify things a bit and not confuse them any further. If not, let's look at an example to actually illustrate the entire point. So let's look at an example. Nitric acid can be formed by the partial oxidation of ammonia with air. In a given reactor, we have NH3 being fed at 25 degrees and preheated air at 750 degrees. And they are reacted at 1 bar, and we've been given a conversion of 90% of NH3. And the reactor output is 920 degrees Celsius. And they want us to calculate the required rate of heat removal per 1 mole of ammonia fed, assuming a feed of 2.4 moles of oxygen per 1 mole of ammonia. Okay, and we've been given a figure down here, and we have our reaction as well, 4NH3 plus 5O2 giving us NO and H2O. Okay, and as you can see, there are 2 inputs, 1 output at 920 degrees. And as we may expect, we should require some heat removal. Okay, now from our figure, it's evident that we have 2 input streams and a single output stream, and we have been given a conversion of 90%. So we can easily calculate our reaction rate, assuming a basis of 1 mole per hour of ammonia. And now that we have the reaction rate, we can look at writing out our energy balance. Okay, so here is our energy balance. dq dt is equal to my R times delta HR. There is a single reaction in this problem, so it's simply one reaction. Okay, plus the summation of my enthalpies coming in, flow input. Okay, so that will be these 2 streams here, minus my enthalpy going out as a result of flow output. Okay, so now we can actually be smart about this. We have temperatures of 25 degrees, 750 degrees, and 920 degrees. So we could choose to actually set our reference temperature to equal to one of these stream temperatures. Now, if we choose a temperature of 920 degrees to be our reference, then our entire integration and summation for these species enthalpies will become 0, because we will be integrating from 920 to 920. Okay, so that's an attractive choice, so let's go with that. So ultimately, I have no output enthalpy in my balance. It's simply the reaction at 920 degrees Celsius plus the flow enthalpies coming in. Okay, so that's the integral of Cp dt of 750 to 920, 750 to 920. And we are told that ammonia comes in at 25 degrees. So ammonia will be integrated from 25 to 920. Okay, now for this particular problem, the heat of reaction for ammonia has been evaluated from a previous example. So we'll just use our value here. If we don't have this value, then there is a way to calculate it. My delta HR at 920 is equal to my delta HR at 25 degrees plus my integration from 25 to 920. Okay, and we can obtain our delta HR at 25 degrees using the heats of formation, of course, and we can integrate for each component. So that's how our delta HR was obtained. So we're just going to take the value here and use it. Okay, we've also been given an oxygen to ammonia feed ratio, so we know what our ratio of moles of oxygen coming in is. And from our air ratio we can assume, or we can calculate our moles of nitrogen coming in. Now substituting these values, it becomes quite simple, and we can simply take our CP values from our tabulated data. Okay, so we have for oxygen 750 to 920, that will only be sensible heat in the gaseous phase. The same with nitrogen, and also the same with ammonia as well. Okay, so we simply need to retrieve our heat capacity coefficients for the vapor phase and substitute it into these integrals and evaluate them. Okay, and ultimately that will be the problem solved. So we simply evaluate these integrals, perform the summation, and we can obtain our desired dq dt. Okay, so yes, over here I've also included the delta HR at 920 is equal to delta HR at 25 plus my summations of my CP values. Okay, and these are of course my stoichiometric coefficients for each species in the reaction from 25 to 920. Okay, so I have 6 multiplied by the heat of formation of water plus 4 multiplied by the heat of formation of NO minus 4 times the heat of formation of NH3 minus 5 times the heat of formation of oxygen, and this will be of course 0. The heat of formation of oxygen is 0. Okay, so this is sorting out my delta HR at 25 degrees. Okay, that's just this part here, and this part here evaluates this summation. Okay, so we look at each species in my reaction. So for my water, I'm taking my water up from 25 to 920. I'm taking my NO from 25 to 920. I'm taking my NH3 and my oxygen. Okay, from 25 to 920. Now in the case of water at 25 degrees, water will be in the liquid state. So I will first need to take my water to 100 degrees and thereafter add my heat of vaporization, and then take my vapor from 100 degrees to 920 degrees using my vapor CP values. Okay, so it can be quite complicated even though it's simply one reaction. Okay, but nonetheless it's a tedious process, but it's not very not really all that complicated really. It's more tedious. Okay, so that is the problem solved. Now let's look at an example of acetic acid being cracked in a furnace to produce ketene. Okay, and this is a multiple reaction system. So we have the first desired reaction, but we also have a side reaction occurring to an appreciable extent. Okay, and they've told us that it is desired to carry out the cracking of this acetic acid at 700 degrees Celsius. Okay, and a conversion of 80% will be obtained, as well as a fractional yield of 0.0722. And they want us to calculate the required furnace heating rate for a furnace feed of 100 kilomoles per hour, and the feed is being input at 300 degrees Celsius. Okay, so we have a furnace, and here's my acetic acid, 100 kilomoles per hour and 300 degrees, and it's being burned in this furnace, and we're getting the following outputs, and we have the following conversion and yield. And we want to find the heat rate, dq dt. Okay, and if we find the heat rate, then it ultimately gives us information on how much of input we require in order to crack this acetic acid. Now, assuming negligible kinetic energy and potential energy, and of course there is no mention of work, so we get the following energy balance equation. So I have my dq dt as usual equal to the summation of R times delta HR reference. So I have two reactions. So here are my two reactions. I have R1 times delta HR1 reference plus R2 delta HR2 at a reference temperature. Okay, and thereafter I have the difference in enthalpy between my output flows and my input flows. Okay, so that's ultimately adding my summation between my output and my input, and as you can see, there are many different species at my output. So how do we go about doing this problem? Okay, so our furnace is at 700 degrees, so we can assume that our output will obviously be at 700 degrees. So if we state, or if we take our reference temperature to be 700 degrees, then it's quite easy to see that we won't actually need to evaluate the enthalpies of the output, because the integral from 700 degrees to 700 degrees will be 0. So we won't need to evaluate any of these, and that's an attractive option. Okay, so let's choose our reference temperature to be 700 degrees. Okay, so it's a single input and single output system, two reactions, and here's my energy balance. Okay, so I have the following. I have my heat of reaction here for the side reaction, and my output has become 0, so I'm only left with my input, and my input only contains my acetic acid. So now it's a case of simply evaluating this right hand side of the equation. Now let's deal with our reactions at 700 degrees. Now I can obtain my standard heat of reaction for reaction 1 as well as reaction 2 at 25 degrees, of course, quite easily, and I can do this by retrieving my heat of formation from my tabulated data. Okay, now both of these standard heats will need to be corrected to 700 degrees because that's our reference. So it's corrected as follows: the heat of reaction at 700 degrees is equal to the heat of reaction at 25 degrees plus an integration from 25 to 700 of each of my species in the reactor. in the reaction. Okay, so for reaction 1, I have 3 species, the CH2CO, I have water and my acetic acid. Stoichiometry here of 1, 1 and -1. Okay, so here it is, 1 of the Cp of CH2CO, 1 times the Cp of water, -1 times the Cp of my acetic acid. And the same principle with reaction 2, my undesired reaction, and that occurs as follows. Okay, now thereafter it's simply a case of retrieving my heat capacity coefficients. Okay, so using my Cp relations for all of my species, I can ultimately solve for these integrals and thereafter ultimately solve for my heats of reaction. Okay, so that will handle these 2 terms. Now I need to evaluate this integral here, and that's also evaluated by retrieving my heat capacity coefficients. Okay, so the acetic acid enthalpy difference can be evaluated. So ultimately I have evaluated this integral. I know my input. I've evaluated the delta HR2 and delta HR1 at 700 degrees. Now all that's left is to evaluate my R1 and R2, and that can be obtained by using my material balance knowledge, by making use of my conversion and my yield. Okay, so that's a simple material balance and solving simultaneously. Okay, so I end up with one equation of R1 plus R2 being 80. And I can use my fractional yield, of course. Sorry, and that was at maximum conditions. So I can obtain R1 and ultimately R2. And once I've done that, I can easily evaluate for my heat rate. Okay, and that's the problem solved. Okay, finally the adiabatic case. Okay, so previously we've solved an energy balance, and typically we needed to find our heat rate Q. Okay, when either Q in absolute terms or dQ dt in rate terms. However, there are of course instances where we actually know our heat rate, but we need to find our temperature. Okay, so the adiabatic temperature is the exit temperature of any unit in question, which would establish under adiabatic operating conditions. In other words, no heat exchange. Okay, an adiabatic system has no heat exchange, so we will have Q dot or our dQ dt being equal to 0. Now this temperature can be determined by solving the energy balance, assuming of course dQ dt is equal to 0. And considering the fact that we work with specific heat capacities and we have heat capacity coefficients and integrals that we will need to solve, which ultimately amount to 4th or 5th order equations, then ultimately this means that we will need to be solving for our temperature by iteration. Okay, and this of course also assumes that our outlets will all be of the same temperature for any given unit. Now if the temperature changes are expected to be small, in other words less than 50 Kelvin, as we've previously discussed, then we could actually get by using average Cp values. And if we use our average Cp values, then solving our integral of Cp dt actually simply reduces to Cp delta T. And if we know our inlet temperature, we can find our outlet temperature. Okay, so that's a much more simplified case. But in cases where we will have a large temperature difference, or we don't know whether the temperature difference is large or not, we will be safest by evaluating our integral. Okay, now let's look at an example in this regard. We have methanol at 675 degrees Celsius and 1 bar, and it's being fed to an adiabatic reactor, and we have a conversion of 25%. So we have methanol converting or dehydrogenating to form formaldehyde according to that reaction. And they want us to calculate the temperature of the gases leaving the reactor, and they've given us some average heat capacities for each of our species. Okay, so we have our reactor here, and it's a simple single input and single output stream. If there were multiple outputs, the temperature of all of those outputs would likely be the same, so that wouldn't cause much difference. But now let's look at our single output. And if we assume a basis of 1000 moles per hour, we can solve our material balances. Okay, we have simply one reaction, so we can easily solve for our overall reaction rate using our typical reaction rate formula for single reacting systems. Okay, so that's our reaction rate, and we can perform our material balance to get my outputs, my stream outputs. Okay, now we have an input coming in at 675 degrees. So we can, of course, select the input temperature to be our reference state. Okay, so we will have 675 degrees Celsius, pressure at 1 bar, of course, and gaseous phase for all species. Okay, so this is looking to be quite a simple problem. Okay, so let's write out our energy balance. We have dq dt equal to R times delta HR at 675 plus my output stream minus my input streams. Now my input streams, I am taking my reference to be 675. So any integral from 675 to 675 will equal to 0. So I don't have to worry about the input stream. I'm only worrying about my outputs. Okay, and my outputs have 3 different species. So I have a summation. Now dq dt, of course, is 0 because we are looking at an adiabatic reactor. So let's work on solving our heat of reaction first. Okay, since I have my heats of formation tabulated for 25 degrees, I can find delta HR at 25 degrees. And thereafter, I can find delta HR at my reference temperature, 675. So that's equal to delta HR at 25 degrees, which is easily found, plus my summation of my stoichiometric coefficients and my Cp values from 25 to 675. Okay, and by making use of our constant heat capacities, this becomes quite a simple solution for delta HR. And once we have that, we simply need to, so we found our delta HR, we found our R, dq dt is 0, we know our outputs, and we have our average heat capacities. So now it's simply a case of solving my energy balance for my temperature. Okay, and the solution is trivial. Okay, another thing to note is that we have our delta HR for 25 degrees to be 20.38. For 675 it's 21.68. And as you can see, it's positive, right? And that means my reaction is, of course, endothermic. And so consequently, under adiabatic conditions, the outlet temperature will actually be decreased because our endothermic reaction is consuming energy. So that's why we have such a low outlet temperature compared to our inlet temperature. Okay, so take note of these little things to make sure that your results are sensible. Okay, if you're not getting any sensible results, it means that something must be wrong with your calculation. Okay, so once you are able to rigorously solve, although the procedure is quite tedious, it is ultimately not that complicated. Okay, so that's the adiabatic case solved. One final note, okay, regarding the degree of freedom analysis. Recall that for energy balancing in non-reacting systems, we counted our stream temperatures as well as my heat input, dq dt, dw dt. We've counted those as variables. We've looked at counting a single energy balance for an entire unit, and other information such as the saturation state as subsidiary relations. And as a matter of fact, for reacting systems, there is no further complication in our degree of freedom analysis. Okay, so whatever you've learned regarding degree of freedom analysis for non-reacting systems, they will be applicable for reacting systems. Okay, so there's no other extra variables in terms of our energy balancing to include as a result of our reactions. Okay, so that's just one final note. Now let's consider the following example. Okay, this is a process whereby we have methane reacting with sulfur to produce CS2 and the co-product H2S. Okay, now let's look at the process. We have methane coming in, and we know the temperature of methane coming in at 175. It's going through a heat exchanger B, and getting heated up to 700 degrees Celsius. We also have sulfur coming in, so that's S8. Okay, and we know the temperature of the input, and it's also being heated up to 700 degrees. Okay, and thereafter, the two components are being fed to a reactor. And there is some heat transfer between this reactor and the surroundings. Either we are adding heat or removing heat. We have yet to find out. But we also do not know what this heat input is. So we don't know the dq dt at the moment. Okay, the products from this reactor are split. And the products are, of course, cooled down, presumably, to 250 degrees. Okay, and it's cooled down by heat exchanger A, and the products split over here as well are also cooled down to the identical temperature, 250 degrees. Okay, and thereafter the products are recombined, and we have the following product stream. Okay, so we have been given a reaction. This is our reaction, and we are also given a subsidiary relation. Okay, so how do we perform a degree of freedom analysis on this process? So let's look at it in detail. Okay, so first an overview. I draw up my degree of freedom table as normal. However, there are certain things I need to consider and include when it comes to energy balancing. Okay, so this is how a degree of freedom table is drawn up when taking into account material and energy balancing. Okay, note that there is a separate calculation for material balancing only, and there is a calculation for combined mass and energy balancing. Okay, so we don't really do material balancing on its own and then energy balancing on its own. Energy balancing is done in combination with material balancing. Okay, so now in the case of our reactor, we will need to perform a degree of freedom analysis by looking at mass balancing only and the combined mass and energy balancing. The same with the splitter. We can consider just the mass balance, or we can consider the combined mass and energy balance. Now with heat exchangers A and B, we simply have streams exchanging heat. So there is no material balancing that happens. So we only have a combined balance here with certain elements of material balancing and energy balancing. Okay, and the same with heat exchanger B, of course. The mixer is as normal as well, so we have our material balance and we can do a degree of freedom for the combined mass and energy balance. Okay, and thereafter we can combine all of this in one process balance, one process degree of freedom calculation. The overall can also be expressed in terms of material balancing only or combined balancing. Okay, now let's firstly look at our reactor. Okay, so we have the following streams. Okay, and there's methane in the stream. And we have S8. And we know what the products are because the products is simply split and recombined to form the following. So whatever the products are here and whatever the composition is here, it will be identical to the products and the composition in this stream. Okay, so we will have CH4, H2S as well as CS2 in this stream here. Okay, so let's count. For our material balancing, we have 1, 2, 3, 4, 5 stream variables plus 1 reaction. So that's 5 plus 1 there. Okay, and for the material balance degree of freedom, we are neglecting our temperature and our heat exchange. Now with the combined balancing, we will include our usual stream variables. Okay, so that's our 1, 2, 3, 4, 5 plus the 1 reaction. And now since we have 3 streams, that each of them will have 3 temperatures. So we have 3 temperatures. And the reactor would of course have an associated dq dt and dw dt. In terms of the number of balances, there are a maximum of 4 different species associated with this reactor. So our material balance is 4. So we write it in both places for the mass balance and the combined. The energy balance we don't include here, but we do include the energy balance here, and each unit will have 1 energy balance. Okay, now let's look at our number of specifications. There are no composition specifications and there are no flow specifications. So the only specifications that we have been given are that of temperature and perhaps our dq dt and dw dt, which we could assume, well, in the case of the reactor has a value, but we could assume is 0 for the other units. Okay, so let's look at our specifications. None of these apply to our material balance. However, we can assume that our dW dt is 0, so that counts for one specification. We are also given the temperature of the sulfur feed and the methane feed. Okay, and we are also given, in terms of our subsidiary relations, we are given a feed ratio between the CH4 and the sulfur. Okay, and that's relevant to the mass balance as well as the combined balance. Splitter restrictions is of course not applicable here. Okay, as well as the mixer temperatures. Okay, so now let's perform the calculation. For our material balance, we have 6 variables, 4 balances and 1 subsidiary relation, so that leaves us with a degree of freedom of 1. Okay, in terms of our combined balance, we have 6, 7, 8, 9, 10, 11 variables. We have 4 plus 1, 5 balances, 3 specifications and a subsidiary relation. Okay, so let's count it. We have 4, 5, 6, 7, 8, 9 and 11 variables, so that will give us a degree of freedom of 11 minus 9, which is 2. Okay, now let's turn our attention to the splitter. For our splitter material balance, we have 3 species in the feed stream, and there will of course be 3 in the products, so that's 3, 6, 9 stream variables. Okay, and we neglect our temperature and our heat exchange for the material balance part. For the combined balancing, we have my 9 stream variables. There are 3 stream temperatures, and we have the dq/dt and the wdt. Okay, for our material balances, there are a maximum of 3 species, so that will make 3 balances, and that's included in the material balance and the combined, and we have 1 energy balance for the combined case. In terms of our specifications, dq/dt and dw/dt, nothing was said about it, so we can assume that both of these values are 0, so that counts for 2 specifications. Okay, so in terms of our temperatures, none of the temperatures are actually specified when being associated with the splitter. In terms of our subsidiary relations, the feed ratio doesn't apply. My splitter restrictions, however, do apply. Okay, so I have 3 components and 2 splits, so that's 3 minus 1 multiplied by 2 minus 1, so that will give me 2. And that's applicable to both the material balance and the combined case. A further subsidiary relation for a splitter in terms of the energy balancing is that this is simply a splitter, so whatever the temperature is in our feed, we will have the same temperature in our products. So if we know one temperature, either of the feed or the products, we will know all of the temperatures. Okay, so that can count for 2 subsidiary relations. Okay, we can say that, for example, this T of the feed is equal to this temperature here, or T of the feed is equal to this temperature here. Okay, so they are all equal, and that accounts for 2 subsidiary relations. Okay, so let's perform the calculation. We have 9 minus 5, so that's 4 for the material balance. And for the combined case, I have 9, 10, 11, 12, 13, 14 variables. 3, 4, 5, 6, 7, 8, 9, 10. So that also gives me a degree of freedom of 4. Now let's look at our heat exchanger. Okay, in terms of our heat exchanger, there is a special way to handle heat exchangers. Okay, so pay careful attention. When it comes to counting the number of stream variables, in the case of a heat exchanger, we don't count every variable in every stream. Instead, we count the maximum number of different components. Okay, so in case of we have the following here. So we have S8, our sulfur, coming in, so that's one component, and we have CH4, H2S and CS2 in the other stream. Okay, so that will give me a total of 4. Okay, so that's my number of variables for heat exchanger A, stream variables. Now if sulfur had occurred again in this stream here, we would still count it, because we are counting the number of different variables but in the same line. Okay, so we have one variable here, but we could have any number of variables here even though it's the same variable. Okay, so just pay careful attention and try to wrap your head around this. Okay, so that's 4. There are 4 streams here, each of them will have a temperature. So we have 4 temperatures, and dq dt and dw dt are also variables. Now in terms of our balances, there's no need to do any material balance. It's absolutely irrelevant and unhelpful. The only balance we will have is a single energy balance. Okay, so this is true for all heat exchangers of this form. There is no mixing occurring at all. We simply have one stream going in and it's the same stream coming out. And the same with this one here. We have one stream going in and the same stream coming out. So there is no mixing, there's no need for any separation. Okay, so there's no reaction occurring as well. So there's absolutely no need to do a material balance on a heat exchanger. Okay, now in terms of number of specifications, we can assume that dq dt and dw dt is 0, so that counts for 2 specifications. We also know the sulfur temperature and the methane temperature, we know the sulfur temperature, the inlet and the outlet, so that will give me 2 there. This methane temperature doesn't really apply, so that's 0. Okay, now in terms of the feed ratio, that's irrelevant. Splitter restrictions are also irrelevant, as well as the splitter temperature. Okay, in addition to these 2 sulfur temperatures, I also have a third temperature here that's also specified. Okay, so I can just count that as 1. This could have been counted under specifications, or it can be counted under a subsidiary relation as well. Okay, it's important that you don't count it twice. Okay, so let's perform the calculation. We have 10 variables, 1, 2, 3, 4, 5, 6 bits of information and balances, so we have a degree of freedom of 4 once again. Okay, and a similar approach for heat exchanger B. Okay, we again have a maximum of 4 variables. Okay, so we have methane coming in here in this line, so that will count for 1 variable. Then we have methane, H2S and CS2 coming in this line, and those account for 3 variables here, so that's 3 plus 1, 4. Okay, and this is what I was trying to explain a bit earlier. We are counting the number of variables in each line, and since we have the same line going in here, so that's 1 variable, methane. Even though we have methane here, we still count it again because it's in a different line. Okay, in terms of our temperatures, we have 2 inputs and 2 outputs, so we will have 4 temperatures. And once again, the dq dt and dw dt. Once again, there's no material balancing. There will be just a single energy balance. We can assume dq dt and dw dt is equal to 0, and that counts for 2 specifications. We don't have to worry about the sulfur temperature here. That's irrelevant. However, our methane temperature is relevant, and we have 2 temperatures for methane. We have this 175 and we have 700 degrees in this line. So that's 2 temperature specifications. Okay, and just like how we have for heat exchanger A, the feed ratio, the restrictions are all irrelevant. However, we do have another temperature here, 250 degrees specified for the mixer. Okay, and that once again gives us a degree of freedom of 4. Okay, so that's 10 minus 6, 4. Finally, let's look at our mixer. We have 3 streams and 3 variables for each one, so that will give us 9 stream variables. In terms of our temperature, we ignore that for material balancing. But we have 3 streams, so that accounts for 3 temperatures for our combined balance. And we can count our dq dt and dw dt. In terms of our material balance, there are a maximum of 3 components, so that's 3 material balances, and of course 1 energy balance counted here. In terms of our specifications, for our material balancing, all of my temperature specifications are irrelevant. My feed ratio in terms of my subsidiary relations are also irrelevant, as well as splitter restrictions, temperatures. So that's my material balance degree of freedom. 9 minus 3 will give me a degree of freedom of 6. Now let's look at the combined balance. In terms of the number of specifications, we can assume dq dt and dw dt is 0. So that counts for 2 specifications. The sulfur and methane temperatures are irrelevant here. The feed ratio is irrelevant, as is the splitter restrictions and the splitter temperature. Okay, now let's look at the final subsidiary relation for the mixer. Okay, so we have actually 2 feed specifications, 250 and 250, so that will count for 2 specifications. And a further subsidiary relation in this particular case is that since these 2 temperatures, the 2 feed temperatures, are the same, my output temperature will also be the same. Okay, so I can count it as 3 specifications. So I have 1, 2, and 3 temperatures known. Okay, and that's why I'm counting it as 3 there. Okay, and now to perform the calculation, that's 9, 10, 11, 12, 13, 14. And here I have 4, 5, 6, 7, 8, 9. So 14 minus 9, that gives me a degree of freedom of 5. Okay, and now for the relatively difficult part, counting the balance for the process. And because we are going the approach of looking at our combined balance, we need to now add up all of our variables. Okay, so now let's look at it one by one. Okay, now in terms of variables, now recall that this stream here is simply passing through the heat exchanger. So in terms of our material balancing, this only counts as 1 stream, and the same for these streams here as well. Okay, so let's look at it. We can count our variables. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so that's 14 variables plus 1 reaction occurring in the reactor. Don't forget about that. So that's 14 plus 1. In terms of our temperatures, we have the following. Now, in terms of our actual material balancing, these are the same lines. However, my temperatures do change, so I do need to take that into account. Okay, so let's look at it. We have 1, 2, 3, 4, 5 temperatures, 6, 7, 8, 9, 10 temperatures. Okay, so that's 10 temperatures for the process. In terms of the dq dt and dw dt, I have 5 units here. I have 1 reactor, plus the splitter, the mixer, and 2 heat exchangers. So that's 1, 2, 3, 4, 5. Each of them have an associated dq dt and dw dt. And so these account for 10 variables. In terms of my material balancing, I can count, and I need to count this only once. So just add up all the material balance parts. I have 4, 5, 6, 7, 8, 9, 10. 10 material balances. In terms of the energy balancing, now we only count the energy balances. So I have 1, 2, 3, 4, 5. Okay, so that's equal to the number of units I have in my process. In terms of number of specifications, for dq dt and dw dt, I have 5 units, and 4 of them I have assumed to have dq dt and dw dt be 0, and we've assumed dw dt is 0 here. However, we still need to find dq dt. So that ultimately leaves us with 9 specifications. So 4 dq dt and 5 dw dt's are equal to 0. Okay, it's just 1 dq dt for the reactor that I need to find. Now, in terms of my sulfur temperatures, I've been given 2 temperatures. Okay, so that's 1 there and 1, so that's 2. In terms of methane, I've been given 1 and another, that's 2. So adding it up there, I've also been given, in terms of my subsidiary relations, 1 feed ratio, 2 splitter restrictions. The splitter temperature is also counted, as well as my maximum 3 for the mixer, okay, due to both of these temperatures being equal. Okay, so we have, in terms of our number of variables, that's 35. Let's count our other specifications. So I have 10 plus 5, that's 15, plus 9 is 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 36. Okay, so my process is actually over specified. 35 minus 36 is minus 1. Okay, so we do ultimately have more than enough information to actually solve this problem. Perhaps we have extra information and we may end up with some inconsistencies. Okay, now finally let's look at our overall. Okay, in terms of our material balancing, my inputs and outputs are all here. So I have 1, 2, 3, 4, 5. So that will be 5 there. And of course 1 reaction. So let me add that. Okay, and I will add the same for the combined balance. And for the, in terms of temperatures, these are 3 lines here, so that's 3 temperatures I'll need to worry about. And in terms of dq dt and dw dt, I will have to consider the total dq dt and dw dt over the entire process. Okay, so that will count for 2 variables as well. Now in terms of the material balancing, okay, I have 1, 2, 3, 4. That's the maximum number of variables associated with the overall balance. So that's 4 there. And once again, 1 energy balance. Okay, in terms of my specifications, dq dt cannot be 0 because we are told that the reactor dq dt is not 0 and we need to actually find that. However, my dw dt over the entire process is 0 because it's 0 for each and every unit. So I have 1 specification here. I know my sulfur temperature and I also know my methane temperature. Okay, so that's that and that there. My feed ratio also counts as a subsidiary relation here. It's relating both of my feed streams. Splitter restrictions don't count. And now in terms of my mixer, due to the fact that these 2 temperatures are the same, I can say that I also have this temperature here specified as well. Okay, so that's as follows. So let's do the calculation. I have 6 minus 5, so that's 1. And here I have 6, 7, 8, 9, 10, 11. And I have 4, 5, 6, 7, 8, 9, 10. So 11 minus 10, that's a degree of freedom of 1. Okay, and that's the problem solved in terms of the completion of the degree of freedom analysis. Okay, now as you can see, we can't really solve any of the individual unit balances, but we do have more than enough information. My biggest guess is that, well, my best guess is that we probably have too much of irrelevant information, whereas we actually don't have more relevant information such as the actual feed flow rates. Okay, so ultimately we will need to assume a basis in order to solve this problem. Okay, but the reason for this example was to illustrate how we draw up a degree of freedom table. Okay, so that's the degree of freedom analysis solved.